Hello, everyone, and then welcome to another session of the waimm webinar series. Today, we're going to have a waimm Distinguished Lecture. The waimm Distinguished Lecture is a master class series of lectures given by fellows and highly distinguished personalities in the industry. Over the years, we've been having a couple of them. And today is another master class lecture. We're going to have Professor Kwasi Amankwah. It's actually Richard. He's a professor in minerals engineering from UMAT. What makes it more distinguishing is a newly appointed VC of UMAT. Prof is a master of this subject. He's actually a serious authority on this one here, from geometallurgy to everything that happens in the plant. I'm going to be your host for today. My name is omari-mensah. I'm the president of waimm. As always, sit back, relax, enjoy the next 1.5 to 2 hours. Prof, it's all yours. Take it away.
Thank you very much, President. And good afternoon to everybody on this platform. My name is Richard Amankwah, and I'm making this presentation on reducing uncertainties in communication circuit design and operations. This is a study being done with Charles Amankwah, the GM of Asanko, currently a vice president even. Right. So we would look at the uncertainties in the minerals industry. We will consider some of the design issues regarding communication circuits. We will look at throughput and grind challenges, which we face every day. And we will look at 3 case scenarios about how to reduce uncertainty. And we will look at some final comments. As we are all aware, investments in the minerals industry normally depend on the tonnage available. And we are looking at uncertainties associated with issues in the minerals industry. We'll consider some design issues and talk about throughput and grind challenges that we face every day. And we will see how we can reduce some of these uncertainties based on work that has been done in several processing plants. And I'll give some final comments. We all know that investments and development in the minerals industry happens to be dependent on the tonnage available and also the grades. And there are so many uncertainties associated with determining some of these variables, mainly because of the fact that there are uncertainties associated with the ore body itself, whether it is homogeneous, heterogeneous, and some geological processes that sometimes are not very clear to human beings. And of course, sometimes some inaccuracies in the gathering of geological data and then also measurements. These uncertainties sometimes bring challenges, and human beings try to find solutions. In the geological and mining arena, several models have been developed. People use geostatistics, fuzzy logic, neural networks, and over the years, some codes have been developed, some from the US, Australia, Britain, several places, which will guide strategic decisions and investment planning. But normally when it gets to the minerals industry, especially when you go to the plant, we don't have many models that help us to reduce uncertainty in the design and operation of communication circuits. And therefore, this presentation is about some of the work that has been done and how we can maybe steal some ideas here and there to help us to run our communication plants. Some relevant questions come, and maybe these are rhetorical. Is your communication plant or circuit giving you the tonnage for which it was designed? There are times you design a comminution circuit to deliver 1,000 tons per hour, and for 6 months, you have not even been able to get 900 tons. Do you have constraints on your screens? How do you select your screens? For instance, is your SAG mill generating excessive amounts of scuds? And are you thinking of going for a second pebble crusher? Are your mining pits becoming deep? And does it make comminution difficult? These conditions require the development of appropriate models to solve them. Conventionally, when people in the projects team are asked to develop a comminution circuit, the normal thing would be to go for core samples, sometimes quarter cores, half cores, and the grindability is established, the crushability is established, and also the abrasive index, so that we will know the energy that is required to go into the comminution circuit, in addition to how the rocks would play on the liners regarding wear. These properties work very well, but you and I would agree that all characteristics change as we move from one horizon to the other. And it gets to a point where the initial inputs for the development of the plant virtually become null and void. And it becomes necessary to rethink this whole business. There are times as pits become deeper, rocks become harder, they impact negatively on mill throughput. And for most processing plants, if something like that happens, the rocks have become harder, bond work index has changed, and therefore the available energy from the mill motor is not able to grind to the size that we want. One of the simplest ways would be to push in additional energy. Go for some mobile crushers, crush finer, so that we can feed the system and get it going. Since we know that sometimes you may have to bring in a mobile crusher, or sometimes you may even think of a secondary crusher to support the SAG mill operations, it is important that we think through this process before we hit the ground to design the plant. Because in some cases, maybe 5 years down the road, 10 years down the road, you'll still have some ore available. They have become harder. You want to bring in a secondary crusher, but the space has not been made available for such a machine. You don't have the footprint. And even if you have it, sometimes the place where you will put your conveyor so that this secondary crusher can be fed and also for it to deliver its product, and becomes a problem. So in designing of such plants, it's important for us to look ahead and find out all the possible issues that can happen. And even if we cannot make provision for that immediately, let's know that maybe in 5, 8, 10 years' time, it is possible this situation would crop up and we may have to make room for that. So you go in for more energy, you inject more capital, sometimes unplanned, and these things require that we rethink to avoid setbacks. Let's look at the typical horizon. You have the ground surface, you have the weathered material at the top, the iron oxide cap, the leach zone. But when you start drilling, most drilling campaigns would go down to between 200 and 300 meters. And rightly so, because you cannot stand at the surface and drill down to 1 kilometer to take cores. That is practically not possible. But if you are able to get drill cores from between 200 and 300 meters, then it will help you to predict the type of material that you have to process and the strategies you can put in place to take care of it. The question happens, or the question comes up that, assuming you drill to 250 meters and you use the information available to design your plant, what happens if the pit becomes deeper and you go down to, let's say, 300? or 350, because these are realities. Pits can go down sometimes even to 350, 400 meters. The fact that you did not take samples at that depth to analyze them and to incorporate them into the plant design brings an uncertainty. So how do we handle such uncertainties? And what effect has it got on the comminution circuit? Let us consider some studies that we have conducted and some new approaches that people have brought up. And in my case, some of the research I've also done in the area. We looked at a plant where before the design came up, drilling was done up to 273 meters. And the mineralogical investigations were done and the geometallurgical mapping was developed. The recommendation was a SAG ball mill circuit, subsea. And after running the plant for about 5 years, we realized that the plant could not deliver the tonnage that it was expected to deliver. An expansion project was commissioned, and for the initial 6 months after expansion, problems, and more problems. Can we avoid such situations? By looking ahead in our design. These are some mineralogical investigations that were done as part of this study from the core samples that came. And you can see that we have fresh material. This is maybe sample A. You can see that the minerals are predominantly feldspar and quartz, making up almost about 80% of the material. This is fresh material. And from the geometallurgical point of view, this is going to be a very hard rock, fresh rock. And the bond index of these materials were always above 16 kilowatts per ton. Then this profile also was developed where we had minimal quartz, minimal feldspar, but a lot of goethite, that is iron hydroxides, hematite, kaolinite, pyroxene, chloride. These are all very weathered material, very soft material, indicating that some parts of the ore body were very weathered and soft, sometimes with work indices below 10. And then you have the very hard ones with work indices beyond 15. And then we have the transition material, which have a mix of hard rock and soft rock together. If you see the mineralogy this way, then we have to be informed that we have to plan ahead, looking at the fact that we have a lot of fresh rock, which would one day require excessive energy to reduce particle size. These ones are easy, you can always grab and then mill easily without a problem. But the fact that we have some ores that contain about 60% feldspar, very hard rock, almost about 15% quartz, also very hard, gives us an indication that we have to plan and make provision for hard rocks along the line. From that study, we took about 45 core samples down to a depth of about 242 meters. And we performed bond work analysis on each of the core samples and came up with a relationship between the bond work index and the depth. Excel gave us a nice equation coming up. Thank God I didn't have to do this calculation. It is normally known that if you are using a polynomial equation, the more you go up on the order, the higher the accuracy, because the R squared becomes better. But in this discussion, we realized that after modeling with a polynomial of order 2, 3, and 4, the order 2 was the best because it had a lower error. For the order 2, the mean square error was 0.5 and the root mean square error came up. But for the order 3, the mean square error became much higher, that is 2.4. And for order 4, it was even much worse. So after running the statistical model, we arrived at the fact that it is better to use an order 2 for the polynomial to come up with the equation. And this is what you see in the graph here. This is the process that we went through. Normally in this statistical modeling, you start with a training data, which will take about 80% of the data that you have, and you develop. So out of the various core samples that we had, from a depth of about 14.6 meters down to 240 meters, we developed the bond work indices in the lab and then used the equation that we have developed to predict. And it came out clearly that there was some amount of relationship between the predicted and then the one that was observed by ground truth. The error margins were developed and the error squared comes here, giving us a mean square error of 0.7. The root mean square error is here, and the various parameters to check for quality are also here, the R squared. After working with the 80% of the data, we wanted to validate the results on the remaining 20% to see whether this equation works well for us. So in the validation model, we worked from a depth of 243 meters right down to 273. And these are the ones obtained in the lab, and these are the ones that were predicted. It can be seen that there is near parity between them. For instance, here, the one developed in the lab gave us 15.1 as bond work index, and the predicted one was 15.2, giving an almost close figure. Some of them went off a little bit, but to a large extent, the mean square error was 0.5, which is very acceptable in situations like this. Based on the success of the validation work, we try to find out, assuming you drill down to 273 meters, and you want to find out what will happen as the pit goes deeper. For instance, what would be the work index at 280 meters, 300 meters, 350 meters? And it was realized based on the model that if you intend to drill or work on your pits to a depth of about 350 meters, you should expect to meet rocks of hardness about 19.7. This means that it is important that when you are building your plant, 350 meters down would be maybe, depending on the way the mine plan is, it can be 10 years down the road, 5 years down the road, depending on the pit development. But the metallurgist should have it in mind that one day along the line, if the plant doesn't close down, you meet rocks of hardness about 19.7 BWI, that is the bond work index in kilowatt hours per ton. So the question is, will your plant be ready to handle such material in case you get to that point? If you cannot budget for that immediately, can you at least leave a footprint where possibly you may mount a secondary crusher, or you can get a set of mobile crushers to do this work so that you can take care of the rocks that you will meet down there? The advantage we saw with this modeling is that instead of using a drill to move to about, let's say, 273, and after you are finished with your work at that level, mount another drill and go down to 350, you could do up to 273 and then model the rest. The savings are that for those of you who are in drilling, it is clear that the approximate cost of carrying out a diamond drill campaign is about $250 per meter. It varies from one region to the other, of course. And reverse drilling is about $100 per meter. So by using this model, it comes to show that there is big savings. By moving to even 250 meters, it will cost you about $62,500. And then you model the rest up to 500 meters, and there are big savings in both diamond drill and then reverse drilling campaigns. And therefore, this model would bring big energy savings and big money savings in particular if we decide to model the results that we get up to the initial drilling campaign level and then try to find out what we can get as the pits become deeper. There are also some other matters arising. So the issue is, does the mine intend to develop the pit to a depth of, say, about 350 meters? If so, then the work index could go up to 19.7. Can the circuit handle it? SAG mills are not designed for very hard material. And therefore, when you put in materials that are hard, in mineral processing, when you say that the material is hard, we are looking at bond work index about 14 kilowatt hours per ton. And therefore, when we talk about 19.7, it means that we are almost getting to the very hard zone. And SAG mills cannot handle this material. In that situation, how can we help the plant to work? We will look at some scenarios, and then we will see how best we can go around it. One major thing is that if the mills are not working very well, it means that circulating load becomes extremely high, especially if you don't cut back on tonnage. But the question is, which mine in this world at this time really wants to cut back on tonnage? Everybody wants to increase tonnage because grades are low and most plants are tonnage driven. So it is important to see or do some more detailed analysis to find out, is it that the material that you are getting is uniform and therefore the work index is attributable to virtually all the material, or there are some individual rock types that are very hard? This question is important because it will inform sometimes the kind of method that you have to use. And these are critical questions to answer. And in answering them, we come up with some models. The mill motor has some constraints. Anybody who has worked as a plant design person or a project metallurgist is very familiar with this equation. It's a very basic equation in minerals engineering. We are saying that the energy that goes into buying, or let's say the mill motor, is normally this E, the energy that is available for milling, and it's equal to 10 times the work index into the 1 over the square root of the product particle size minus 1 over the square root of the feed particle size times the tonnage, thanks to bond. So it means that in a situation where we have fixed energy E, the mill motor has already been bought, installed, coupled to the mill, giving room for about 10% for pinion transfer. It has been established. So the energy available on the plant is fixed. So if work index becomes higher as you go deeper in a pit, then it means you may have to sacrifice either the product particle size, the feed particle size, or the tonnage. Most mines will not want to sacrifice tonnage. Push the tons. That is the order of the day. Can we sacrifice product particle size? If it is a leaching plant, the material is going for leaching. Maybe we want 106 microns because that will help us to leach well within 24 hours and deliver the goods. So we don't want to touch it. So the feed becomes one area that we can touch. And another one is, can we find a way of modifying this work index so that by the time it moves from the pit to the plant, in anticipation of hard rocks, we have to do good mine planning. And apart from that, it is important that we create appropriate scenarios. The first scenario I'm talking about is the mine to mill concept that helps us to solve the problem in the pit. And the two other scenarios, the 2 and the 3, we have planning with a secondary crusher where the rocks are virtually similar in hardness, and then the segregated crushing system where you have some rocks that are very hard and you have some rocks that are relatively soft. The mine-to-mill concept has been very well developed over the years thanks to great researchers in the field like Eloranta, who came up with some of these initial concepts. In the mine-to-mill concept, we say that you can change the work index by changing the powder factor for blasting. That means that you modify the properties of the material inside the pit before it gets to the plant. Work that has been done by several researchers show that for a mine with an in-situ rock strength of about 14.5, it is possible to drop the work index from 14.5 to almost about 4 just by changing the powder factors. The miners will talk about specific energy. So here we are trying to look at changing the specific energy used in blasting so that we can get smaller fragments. It's not only smaller fragments that we are looking at, but depending on how the bench heights are developed, we can get more energy into the rocks, which will generate micro cracks. And the micro cracking makes it easier for the material to be milled. So, of course, I don't expect anybody to increase powder factor to about 1.6. That may even pull down the offices of the mines. But I want to believe that if you can reduce the work index from 14.5 down to even 10 or 8, so long as the range of powder factors is within that which your environmental protection agency in the specific area would allow you to work. I'm talking about the ground vibration. If the ground vibration can be controlled whilst you increase the powder factor, then we can have a situation where we can increase powder factors and bring down the work index. That means that we are dropping the work index inside the pit before it gets to the plant. Fundamentally, there are 3 ways by which we can change energy consumed on a processing plant. And that is what the mine-to-mill concept addresses. You can change the feed size to the primary crusher. If, let's say, initially you blast and your PAT after blasting is about 800 mm, and based on the 800 mm, you'll have a primary crusher that is supposed to discharge 150 mm. Then it means that if you're able to generate more 150 mm through blasting, then a lot more material can bypass the primary crusher. And then you can save some energy for the primary crusher and also make more material available for the next stage of the operation. Again, you can decrease work index by additional micro and macro fracturing. And that is what we were talking about by increasing powder factors and making sure that you drop the work index inside the pit before it gets to the plant. And once the feed sizes have been reduced, then you can bypass several stages of crushing. So for instance, if originally your PAT after blasting was 800 mm, and you are able to bring it down to, let's say, 600 mm, and then create more fines lower than 150 mm, which is supposed to be the primary crusher product, then it is possible that you can bypass about 40% of the blast material by the primary crusher. And a good percentage of this same material can also bypass even the secondary crusher if you have one. But if you don't have it, and this material goes to a SAG mill, it makes it work better because you have some fines that are helping to give you a good slurry or viscosity to help with the milling. The mine-to-mill concept is excellent, and it works very well, and it has worked very well in many mining companies. At the personal level, I've helped with mine-to-mill concept establishment in about 3 different mines, and in all cases, it worked well. One challenge that I have found with the mine-to-mill concept, which we may have to think about as we apply it, is the fact that in some areas, the gold occurs in very weak zones. And therefore, as you blast, those areas fragment finer by virtue of the fact that they are already weak zones. So sometimes When it becomes that fine, then it becomes possible for these fines to be lost in transportation so that they do not get a chance even to report on the wrong part for feeding into the processing plant. So there's a potential for excessive reduction of rock size to lead to grade reconciliation challenges. Recently, I was part of a team that helped to resolve one problem on a mine. After blasting, the grade was very high. Let me give it a hypothetical figure. Underground stuff, 6 grams per ton. By the time it gets to the ROM part, the grade gets to almost 4.2 or less. As usual, there'll be fights at morning meetings, everybody trying to blame the other person for not giving the right figure. But during the study, we realized after sizing the blasted material that about 26.8% of the material was less than 2 millimeters. 6.8% of the material that was below 2 millimeters actually held 27.6% of the gold in the ore. And these 2 millimeters material, or less than 2 millimeter material, were very goes through a series of things, skipping, tramming, discharging from the ore pass, and all those things. And by the time you get a chance to load it into trucks from the surface bin, you have lost virtually all the minus 2 mm material as droppings from machines. So by the time it gets to the ROM pad, you have lost almost about 25% of the gold. So the metallurgists think that the miners are not giving them the real figures, or the geologists are not giving them the metallurgists think that the miner is diluting the ore before bringing it to the ROM pad. And morning meetings were very nice. Emotions were high. But it all boils down to the fact that we have to assess what is going on and be sure that we are not losing gold just by trying to blast very fine. So this is one thing we have observed with the concept that we have to rethink as we apply it on a day-to-day basis. Laurentius research has indicated that as we apply the mine-to-mill concept, we reduce processing costs because the rocks become softer, and therefore we can grind more at lower cost. Of course, your drilling and blasting costs would increase, but we all know that grinding is one of the most expensive operations on a processing plant. And therefore, if you can even save 5% in grinding cost, and you increase drilling and blasting costs by 20%, it is still savings. And at the end of the day, the total cost of running the plant becomes lower. So the mine-to-mill concept is very good, and we have to apply it, of course, with the caution that I have indicated. Another scenario that comes to play is when you have individual rocks with minimal variations in work indices, where, for instance, you are going to feed your mill, and from Bond's equation, you know that if I feed material of size, let's say 50 mm to my mill, I'm sure to get my discharge of 106 microns because the energy available can support that. If that works for you, and you realize that your SAG mill needs finer material, then the best would be to possibly consider a secondary crusher, so that after primary crushing, you reduce the material size to the calculated size before you feed your mills. This size you can always get from the Bond equation, which we will look at again. This model is good. It looks only at size and not the work index. Many mines have tried it with success. One major problem that we have to think through as we apply this method is that we have to make provision for a footprint for a secondary crusher as we design the plant. Because if we go ahead and design the plant without making room for that secondary crusher. Then by the time the rocks become hard and we need to install a secondary crusher, we would realize that there is no position for it on the plant as far as the design is concerned. There is no way by which we can build a conveyor belt system from the primary crusher discharge point to the secondary crusher, and even there's no direct link to build a conveyor to feed the sag mill. That becomes a problem. So it is important as metallurgists and of course as plant designers that we try in the drawings to leave a footprint for a secondary crusher, even if at the beginning we would not need it. So that one day, if we have to put a machine like that there, we will not be found wanting because there's no pathway to install conveyors. Let us look at the last one, that is the third scenario, where we have rock types with very wide variations in work index. There are times on a particular concession, you may have your weathered material with bond work index, sometimes even below 10 kilowatt hours per ton. And you may also have some materials with bond work index as high as 15. And this means that the bond work index has become a major variable here. It is not just enough saying that we have reduced particle size, and therefore when it goes into the mill, it should be able to grind fine enough for us. Because the energy required to grind material of size of work index above 15 is totally different from the energy required for material of work index below 10. So it becomes necessary for us to consider the equation again. In a little simulation that I did, this is still the work index, the work equation. The energy available from the motor of the mill is equal to this. For a scenario where you are processing 1,000 tons per hour on a plant, and your anticipation is to get a product size of 106 microns, and you have a fixed motor or energy of 12 megawatts, it means that if the work index is 13, as you can see here, then it means that you can comfortably work with a feed size of 50,000 microns or 50 mm, and you can still generate your PAT of 106, no problem. But just by changing work index to 14, it becomes necessary that you get a feed particle size of 8,000 microns or 8 mm to feed your circuit if you are anticipating that you will get your product PAT of 106. It means that you cannot just throw all the material into one secondary crusher and expect that at the end of the day, you achieve the feed particle size that is required for milling. That is where the segregated crushing comes in. This Excel sheet with the appropriate data shows that for the scenario that we are looking at, energy available is 12,000, product particle size 106 microns. If the work index is 11 and you give it a feed particle size of 30 mm, you are sure that you get your more than 1,000 tons per hour. As the feed particle size increases from 30,000 microns or 30 mm through to 65 mm, there are slight reductions in the tonnage, but the process is extremely sensitive to the work index. So as work index moves from 11 even to about 13, there's a drop of almost about 100 tons per hour. If it goes to 14, you are losing almost about 200 tons per hour. So work index is very sensitive here. That means if you are expecting to get 1,000 tons per hour, then you cannot play with the sizes and say, all my particles are of size 40 mm, go inside and come out as 106 microns. It is important for us to look at each of the materials of various work indices, especially if we can mine them separately or they collect separately. so that we feed them into different mobile crushes. So for instance, you have material of work index above 15. And you know that for this material, I need to crush down to almost about 12 mm before I feed my plant and get a product particle size of 106 microns. For the welded material, even if I throw in 80 mm, I'm sure that by the time it comes out, it will still be 106 microns. For the 13 bond work index, I know that if I'm able to get a size of 50 mm, then I can get my product particle size of 106 microns. So this becomes a little bit expensive, but then it helps you to run a very good plant, and you can go to sleep while the plant works, because the hard material of work index above 15 has been crushed to maybe 12 mm already. The welded material is coming in at maybe 80 mm, and this material of 13 work index is coming in at 50 mm. So 12 mm here, 80 mm here, 50 mm here, all get onto the crushed ore stockpile. And all these, by calculation and design, you are sure, would give you 106 microns when it gets into the mill. This is what I would refer to as a segregated crushing system. And it is one of the approaches you can use. When pits become deeper, rocks become harder, but it becomes clear that the hardness is not general across board, but it is some specific rock types that are actually giving you that hardness. And those rock types can be mined and collected in specific places on the ROM pad so that they can be treated separately. My final comments. In this presentation, we looked at ground truthing and modeling of bond index data from drill cores. And based on that, a model was developed which brought about some savings from a drilling campaign so that you can predict what will happen down there as the rocks become harder and the pits become deeper as well. And it tried also to reduce the uncertainties associated with increases in rock strength and their influence on a milling circuit based on the three scenarios: the mine to mill with caution, the case of the secondary crusher, which requires that we give space in the plant design for it. So for instance, based on the mine plan, you know that in 5 years' time, we are going to reach this zone. So maybe by the end of the third year, your next major budget should make room for a secondary crusher, which has already got a footprint. And therefore, there will be no problem with conveying in and out of that space. And then the segregated crushing system that allows you to reduce each particular rock to the size, which is such that when it goes into the mill, it will give you the appropriate product particle size. Let us create and share other scenarios, and let's all think through and leave footprints for future changes. And thank you very much. That is Richard Amankwah reaching you on the waimm platform. Thank you.